Autoregressive normalizing flows. Bayesian optimization is a method to efficiently optimize the black box function fx. In our case, the goal is to find the input that maximizes this function. It's widely used in applications like automated design, drug discovery, and more. The function we are trying to optimize is often expensive and complex. And it is a black box function. We can evaluate it, but we don't know about other information like gradients. And this is where Bayesian optimization comes in. It uses a probabilistic surrogate model. This predicts the objective with uncertainty. Then we have an acquisition function. It uses a surrogate model to decide where to evaluate next. We pick the point with the highest of acquisition function, and like this red point, and evaluate the objective function, like this. And then we repeat this process, search, evaluate, and update until we find the optimum. But in many real problems, the feature set is often complex, like structured or discrete. In that case, latent Bayesian optimization can be a solution of this. Latent Bayesian optimization performs Bayesian optimization within the latent space. For this, use a generative model like a VAE to map inputs into a latent space. The figure is the overall process of latent Bayesian optimization. First, the observed set X is encoded to the latent space with encoder Q5, and then conduct the Bayesian optimization based on the latent representation and their corresponding objective values to select the next query point. And the decoder maps the latent to all the next query points back into the input space. The black box function is evaluated at the new input x tilde and update the data. But there is the problem, which called the value discrepancy problem. This one compares on the left and right side is they looks almost the same, but their objective values are actually very different. When we zoom in, we can see small changes that makes the big score gaps. Let's say if we have an input x with a high score y, and here's the corresponding workload. And then what if we pass it through the encoder and decoder? After reconstruction, we get x hat and score y hat can much lower. It looks like reconstruction worked well, but though this is the value discrepancy problem. It happens because the encoder-decoder doesn't reconstruct perfectly. The figure below shows the example of the value discrepancy problem using the objective score distribution. The blue one shows the original scores, and the original one is after reconstruction. In optimization, we focus on inputs have high score. So here we use the data with high scores. As you can see, the objective values are decreasing after the reconstruction. And this is a reconstruction example from this molecular design task. After reconstruction, the objective value is significantly decreased. And we can resolve this problem with normalizing flows. They use a flow and its inverse operation to map between spaces. Our overall NFPO process works as in the figure, which is similar to latent Bayesian optimization process, encoding and BO over latent space and decoding evaluation. At first, take a closer look at the SeqFlow. We propose a flow model for discrete sequence, like text or smiles. To handle discrete data, we used autoregressive normalizing flows. And previous autoregressive normalizing flows were designed for continuous data, or they couldn't reconstruct discrete sequence perfectly. Then we proposed SeqFlow, which can perfectly reconstruct discrete sequences. The figure below shows the encoding and decoding process of SeqFlow. We start from the X, which is the token sequence, and embed it. And after, through the flow, we obtain the latent representation jet. And with the inverse flow, we can obtain the embedding V just as before. And then we convert the embedding V into input X. The point is that after the inter-reconstruction process, the decoded X is exactly the same as the original input. In particular, we ensure the perfect reconstruction by designing the embedding to function token function and as the Lefferts inverse of the token to embedding function. Here we define the embedding function as H and overflow as G. The inverse flow is G inverse and the embedding to token function as the left inverse. That means H inverse of H of X is X. Using the proposition, we show that the entire encoding, that is composition G and H also has a left inverse, and its left inverse is the entire decoding process. This means that X can be reconstructed exactly through this encoding and decoding. And take an example to see how the encoder-decoder works in detail, and show the process that included. At first, the discrete sequence input X, like an atom sequence such as COC, is embedded into the V through the dictionary. And we obtain the latent representation Z through a flow G. And select the next corresponding Z tilde, and apply the inverse flow to get the embedding. And we select the most similar embedding from the embedding set from the dictionary to transform the embedding to discrete sequence. Finally, we evaluate the function and update the data. In this overall process, we focused on this embedding function. We denote this as H, just like before. Proposition 2 shows that the embedding function we designed is injective and its left inverse is embedded to token function. And by proposition 1, this function guarantees that we can perfectly reconstruct the original sequence from the latent space. And lastly, we change the way candidates are selected for the search in the latent space. We present the token level additive candidate sampling, which collectively choose the latent tokens that we have to explore even more. And the selection of the token is determined based on the point-wise mutual information between each token of Z and the sequence X. Specifically, the probability of sampling and perturbing token is given by the equation below, and the point-wise mutual information between the discrete sequence X and the latent token Zi is denoted as omega I. And this PMI value is used to compute the perturbation probability pi I. We conducted experiments on 2 molecular design benchmarks. The table on the left shows the results from the practical molecular optimization, and the right side is the results from the Wacom benchmarks. The number in the table represents the sum of the scores across 23 tests and the rank of this. As seen in both the table and the figure, our NPO outperforms various existing methods, showing its optimization performance. We compare our base generative model TextFlow with our SeqFlow in 2 aspects. First, reconstruction ability, and second, optimization performance. Both models use the same normalizing flow components. We evaluate the reconstruction ability by checking how often the reconstruction value y hat is different from the original value y, which is in the table. As you can see, TextFlow to construct accurately because it uses a biased LSTM-based mapping that isn't invertible. But our SeqFlow achieves perfect reconstruction, as in the table. SeqFlow gets no error across all the tests. And second, optimizing performance. TextFlow actually has more parameters, but it shows similar performance to the baselines because it's reconstruction ability. Our SeqFlow has fewer parameters and reconstructed perfectly, and it performs much better in this molecular design test. It is an analysis of our tasks. The figure on the left shows the PMI values between each token I and the input sequence. As you can see, some of the tokens have relatively high PMI values, and due to the autoregressive nature, the former tokens tend to have a higher PMI values. As shown in the right figure, the model with offline tax generates a higher ratio of distinct candidates, improving diversity in the search process. And as a conclusion, we propose NetBio, which can perfect reconstruction and resolve the value discrepancy problem in latent Bayesian optimization. Thank you for listening.